This is the second lecture. So I'm going to talk about systems of multiple qubits and the tensor product, which is a mathematical machinery used to describe systems of multiple qubits. So let's review the idea of superposition applied to 1 qubit. So for 1 qubit, we said it can take two states, 0 and 1. And if you perform a measurement, measure whatever observable corresponds to 0 and 1, we're going to find either 0 or 1, and the state is going to be this or that right after the measurement. And then a general state that that system can have is going to be some superposition of these two. This type of measurement is also sometimes called measurement in the computational basis. That's a good terminology to have in mind. So what we're going to do next is to think about, let's consider a system of 2 qubits. So this was, let's say, 1 qubit. So let's call this computational basis measurement. Now consider a system of 2 qubits. And again, let's do a measurement in the computational basis. So we do measurement and we measure both of them. So what are the possibilities? Well, the first one can be 0 and 1, and the second one can be 0 and 1. So that leaves us with 4 total possibilities. So we're going to get 0, 0. Let me actually not put the comma. So 0, 0, 0, 1, 1, 0, and 1, 1. So if I perform a measurement simultaneously on my system of 2 qubits, measure this observable, this quantity, again, that's a 2-valued thing. So as an example, think about the spin of a nuclear spin that can only be up or down in some direction, or maybe the direction of a current, or maybe the polarization of a photon. We're going to find either the 0 or 1 for each of them. So for the 2 of them, those are the entire set of possible outcomes. Again, if I want to generalize the superposition principle in the same way, we're going to say that a general state can be some linear combination of these 4 different states. So it's going to be psi, let's call it alpha 0, 0 times 0, 0 plus alpha 0, 1 times 0, 1, alpha 1, 0, 1, 0, 0, 1, 0, alpha 1, 1, 1, 1. Okay, so that's the most general state that a system of 2 qubits can have. It's a direct generalization of the superposition principle. So that was 1 qubit, that's 2. And we can continue with this line of reasoning. So for example, if I have 3 qubits, what can happen? So you make a simultaneous measurement in the computational basis, and now you see the number of possibilities doubles, right? So suppose these are maybe the first 2 states, or the state for the first 2 qubits. And then the third one for each of these can be either 0 or 1. So instead of 4, we're going to get 8, right? So in this case, we had 2 basis vectors for 1 qubit. For 2 qubits, we have 4 basis vectors. For 3, we're going to have 8. In general, if you have n qubits, the basis vectors can take 2 to the n different configurations. And then a general state for this entire system will be some linear superposition of all of these. So it will have 2 to the n of these amplitudes, these numbers, these coefficients that multiply the basis state. So let's work this out, for example. So I can do let's say 0, and then I can do 0, 0, 0, 1, 1, 0, 1, 1. So I put a 0 here, and then let me do a 1 now, and again do all of those. So 0, 0, 0, 1, 1, 0, 1, 1, 1. If I want to write the general wave function, I will write, let's say, sum over. Can imagine maybe can give a notation to each of these. So let's call them sigma 1, sigma 2, sigma 3, each equal 0 to 1. So you have 3 things that can be 0 or 1. That gives 2 to the 3, which is 8 different possibilities. And then that's going to then I have a coefficient, let's call it alpha sigma 1, sigma 2, sigma 3, which multiplies the state sigma 1, sigma 2, sigma 3. So that's going to be 8 different terms with 8 different coefficients. That's the most general state that can live in a Hilbert space. So this, in this vector space, that corresponds to the states of multiple qubits. So again, the analogy with kind of a geometrical system. So again, like ij, where we represent the points as a linear combination of some number times this unit vector plus some other number times the other unit vector. All of that applies. Again, the coefficients are complex. It's just a dimension of this space keeps growing exponentially. It's a very high dimensional space for a large number of qubits. All right. So let's keep going with this. So let's go back to our 2 qubit example, and let's try to think a little bit more about things like normalization probabilities, this statistical interpretation that we talked about for just 1 qubit. So if I write again my general 2 qubit state. So let me write it again. Okay. So then again, the interpretation in terms of probabilities is going to be very similar. So now each of these numbers, absolute value squared, again, these are some general complex number. So this is going to be the probability that if I make a measurement in the computational basis on both qubits, I find 0, 0. I find both of them to be 0. So that's going to be probability of 0, 0. Similarly, this is probability of 0, 1, and the same for the other ones. For 1, 0, 1, 0, and 1, 1. So alpha 1, 1 absolute value squared is going to be the probability of finding 1 and 1 when performing a measurement on both qubits. So again, this implies that the sum of all these probabilities must be equal to 1. So the normalization condition for 2 qubits becomes alpha 0, 0 absolute value squared plus alpha 0, 1, alpha 1, 0 absolute value squared, alpha 1, 1 absolute value squared. That's equal to 1. Okay. So let's work out a quick example. So consider example. Consider a state. Let's say we write psi to be equal to 1 over square root 3, 0, 0, plus 1/2, 0, 1. It's 1 over square root 5, 1, 0, plus some other amplitude, alpha 1, 1 of times 1, 1. Okay, so first, let's say find alpha 1, 1 absolute value squared if the state is normalized. All right, so I'm going to use my normalization condition. So sum of the squares of all of these must be equal to 1. So 1 over square root 3 squared is 1/3. 1/2 squared is 1 over 4. 1 over square root 2. This is actually square root 5. Let's make that square root 5. 1 over square root 5 is 1/5 plus absolute value alpha 1, 1 squared. So I set that equal to 1. So let's just do the algebra. So I guess the common denominator is 60. So 1/3 is 20 over 60 plus 15 over 60 plus 12 over 60 plus alpha 1, 1 quantity squared is 1. This is going to be 20 plus 15, 30, 35 plus 12, 47. So 60 minus 47 is 13. So that's our answer. This number should be that in order for the state to be normalized, which implies that alpha 1, 1 can be e to the I phi times the square root of 13 over 60 for an arbitrary real phi. Okay. So that's, let's say, part A. And part B, saying find the probability that we get 0 for the first qubit. So how are we going to get 0 for the first one? Well, when you perform a measurement on both, right, we have 4 possibilities. We find 0, 0, we find 0, 1, we find 1, 0, and we find 1, 1. Okay, so of all those possible outcomes, 0, 0 and 0, 1 have 0 for the first qubit, and then 1, 0 and 1, 1 have 1 for the first qubit. So probability of, let's say, first qubit 0 is going to be the probability of 0, 1 plus the probability of 0, 0. So 0, 1 probability is going to be that number squared, so it's a quarter. And then 0, 0 is going to be 1 over square root 3 squared, so that's 1/3. So that seems to add up to, I guess, 7 over 12. So again, the interpretation is I prepare, let's say, my system of 2 qubits in this state. So I have that state, that vector in some 4-dimensional vector space describing my state, and I do exactly the same things. I know I'm getting the same state, and then I measure both qubits, and I don't record what I find for the second one. I just write down every time, you know, I find a 0 for the first one, I put a 0. Every time I find a 1 for the first one, I put a 1. And if I do this n times, and n is very large, 7 over 12 times n times, I get a 0 approximately, and 5 over 12 times n times, I'm getting a 1. Okay. Now it helps to introduce a notation that's a little bit more involved. So that's the so-called tensor product notation. So so far we had this this convention that when we write 0, 0, right, the first 0 corresponds to the first qubit, the second corresponds to the next. So there is some implicit association between like the order in that string of bits that we write and a particular qubit. So if the qubits are different, which they are, we have a set of different distinguishable qubits. Let's say the first one is qubit A, the next one is qubit B. If you have more, maybe the next one is something else, qubit C. So these basis states really imply that an order is assumed. And if I want to make that notation very explicit, it's quite helpful to write them like this. So there is a sense where the state 0, 0, which means the first qubit is in a state. So this implies, let me write it. So 0, 0 implies that qubit A is in state 0 of A. There's a 0 associated with A, and qubit B is in state 0 of B. So there is some sense where this is a product of both of them, in a sense that will become clear later. So it's quite helpful to write this as 0 of A, tensor 0 of B. So this less compact notation more explicitly makes it clear that the first bit refers to qubit A, the second bit refers to qubit B. Similarly, 0, 1 is 0A, 1B, 1, 0 is 1A, 0B, and 1, 1 is 1A, 1B. Okay. Now there's nothing that special about these states in the computational basis. So if qubit A is in some states and qubit B is in some other state, so if they're both in some superposition of their zeros and ones, and they're completely isolated, they're not talking to each other, so we know that each of them has a very well-defined single qubit state, then one expects that this structure might go through, and we should be able to write the state of the 2-qubit system as a similar product between a superposition for state A and a superposition for qubit A and a superposition for qubit B. So let's consider this case. So consider two isolated qubits. They're not in any way interacting. Each in a superposition. So qubit A is in this state, let's say psi A, which is alpha A 0 of A plus beta A 1A. And qubit B is again in a similar superposition. So alpha B, 0B, beta B, 1B. Then a natural way to represent the state of the entire system is going to write it in the same way that we wrote for states in the, for basis states in the computational basis, those zeros and one. I can write this psi as a tensor product of this entire superposition with this other entire superposition. So let me write that as psi of A tensor psi of B, which gives me alpha A, 0A, beta A, 1A, tensor alpha B, 0B, beta B, 1B. So if I distribute this through, so I'm going to get alpha A, these are just some scalar numbers, alpha B, so I'm taking this term with this term, then I have 0A, 0B. Then I have alpha A, beta B, 0A, 1B. Then I have beta A, alpha B, 1A, 0b. And finally, I have beta A, beta B, 1A, 1B. Okay. So now my psi becomes alpha A, alpha B, going to the more compact notation, 0, 0, plus alpha A, beta B, 0, 1, plus beta A, alpha B, 1, 0, plus beta A, beta B, 1, 1. So thinking about the representation as column vectors, so psi A has this representation, alpha A, beta A, in, let's say, 0, 1 basis. Psi B has the representation alpha B, beta B, again in the same basis, but of course this is 0A, 1A, and this is 0B, 1B. And finally, psi A tensor psi B, the state where each of them is in a well-defined superposition, each has a well-defined single qubit state, has a representation that I can read off here. So it's going to be alpha A, alpha B, alpha A, beta B, beta A, alpha B, beta A, beta B, in this basis, 0, 0, 0, 1, 1, 0, 1, 1. Okay. Now, so there is a recipe for the tensor product when it comes to matrices. So let's just briefly review that. And then we're going to apply it to this case. So, so suppose we have an n by m matrix A, and let's say a p times q matrix B. Okay, so how do I find A tensor B? Well, the recipe is this. Let's do it with an example. So essentially what I do is I take every element of A, multiply the entire B matrix by that element, and then put it in place of that element. So let's do an example. I don't know. Let's suppose A is A, B, C, D, E, F. So it's a 2 by 3 matrix. And let's say B is X and Y. So it's a 2 by 1 matrix. So the way I would do it is I would write A times XY, B times XY, C times xy, D times xy, E times xy, F times xy. So this is going to be A tensor B, and then I get rid of all the internal parentheses. So this becomes now a matrix that's 4 by 3. So I have AX, AY, DX, DY, BX, BY, EX, EY, CX, CY, FX, FY. So in general, this matrix, if you apply that recipe, it's going to be Pn times MQ dimensional, right? So essentially every element of A is replaced by a P times Q matrix, right? Then that means that the number of rows of A, so in this case, I had 2 rows, is multiplied by P, the number of rows of B. So in this case, the number of rows of B was 2. And then every element was multiplied by that. So the number of rows is multiplied by 2. And then every column, again, becomes P columns. So that's the dimension. So it's a multiplication structure that increases the dimensionality, and that's really appropriate for this case, because as we argued, if I have 1 qubit, it lives in a 2-dimensional vector space. If I have 2 qubits, it lives in a 4-dimensional vector space. If I have 8 qubits, it lives in an 8-dimensional vector space. So if I want to write some representation of these states in terms of their components, I need a multiplication structure that increases the dimensionality, and that the tensor multiplication is a suitable mathematical machinery for this. So just to check that these work, let's go back here. So see, so if you think about the representation here, if I just take this 2-by-1 matrix, this column, and do a tensor product by this 2-by-1 matrix, how would I do it? Well, I would write alpha A, the first element of this, times that entire thing, alpha B, beta B. And I would write the second element, beta A, times this, alpha B, beta B. And now getting rid of these internal parentheses, I find alpha A, alpha B, alpha A, beta B, beta A, alpha B, beta A, beta B. One has to be careful that we arrange the basis states in the same way that follows a tensor product structure. So see, when I write 0, 0, 0, 1, again, I'm doing this a similar construction. I take the 0 and first multiply it by 0, then by 1. So it's like you take 0 and tensor product with this vector with 0 and 1 for B, and then you put 1 and then 0 and 1. So this construction works for this particular order of the basis states. Okay. So we talked about the general superpositions that we can get for 2 qubits, right? So general we wrote them, let's say, as alpha 0, 0, alpha 0, 1, alpha 1, 0, alpha 1, 1 in these spaces 0, 0, 0, 1, 1, 0, 1, 1. And we talked about direct product states. So these were states where qubit A was in a well-defined superposition, and qubit B was also in a well-defined superposition. So we wrote something like as alpha A, beta A tensor with alpha B, beta B. So clearly, any state like that, right? So if you just expand it out, as we did just right now, so let me write it. Any state like this is also a general superposition. So it's just, if you call this alpha 0, 0, call this alpha 0, 1, alpha 1, 0, alpha 1, 1, we're going to be fine. It may take a little bit of effort to show that if these individual single particle states are normalized, then this tensor product is also normalized. So that's something we'll discuss not in this lecture, a little bit later, but that's indeed true. So if these are normalized, that's going to be a properly normalized superposition. But the inverse is not true. So there are states of two qubits that live in this general vector space, which cannot be written like that, which cannot be written as a direct product of single qubit states for the two qubits. So that means that if you think about one qubit in that state, there is no state that you can write to describe it. We really have to work with this four-dimensional space of the two qubits. So let's give an example. So consider the state, let's say square root of 2, 0, 1 minus square root of 2, 1, 0. So that's a state where alpha 0, 0 is equal to alpha 1, 1 is equal to 0. Alpha 0, 1 is 1 over square root 2. Alpha 1, 0 is minus 1 over square root 2. It's easy to check that it's normalized. So these are zeros. 1 over square root 2 squared is 1/2. 1/2 plus 1/2 is 1. So that's a good normalized state for two qubits. And if we could write it this way, then it would imply that alpha A, alpha B, and beta A, beta B must be 0. So let's try and see if we can make it work, right? So if we could write it this way, there were alpha A, alpha B, beta A, beta B, such that this state, another representation for this would be 0, 1 over square root 2, minus 1 over square root 2, 0, such that this state is equal to that state, then we should have alpha A, alpha B is 0, and beta A, beta B is 0. So let's call this psi singlet. has a name. It's called the singlet state for reasons that we don't worry about in this course. So, so if psi singlet is equal to psi A tensor psi B for some alpha A, beta A, alpha B, beta B, then we must have this equality, right? We must have alpha A, alpha B is equal to 0, beta A, beta B is equal to 0. And then we want alpha A, beta B to be 1 over square root 2, and beta A, alpha B to be minus 1 over square root 2. All right, so if I think a little bit about this, I see if that's the case, then I have two possibilities. Either alpha A is 0 or alpha B is 0. And if beta A, beta B is 0, again, one of them must be 0. So I have four possibilities if these two equations hold. And those four possibilities are, well, let's say alpha A is equal to beta A is equal to 0, or alpha A is equal to beta B is equal to 0, or alpha B is equal to beta A is equal to 0, or alpha B is equal to beta B is equal to 0. And now for each of these, possibilities, let's take a look at what these guys can be. So let's do alpha A, beta B, and beta A, alpha B. So alpha A is 0, so this is 0. Beta A is 0, this is 0. Alpha A is 0, again, that's 0. This one is not obvious, we don't know. So alpha A and beta B, but those are not in there, so we don't know. Now let's go to this case. Alpha B is 0, so that's 0. This we don't know. And then in this case, alpha B is 0 and beta B is 0. So these are both 0. So see, in all of these four cases, which are the only cases where I will have these two products to be equal to 0, at least one of these two coefficients is 0, right? So here, yeah, at least one of them is 0 in all cases. So it's not possible to get one equal to 1 over square root 2, the other equal to minus 1 over square root 2. So this is an example of a state that's perfectly allowed. It's a superposition of all these basis states. It's a vector that lives in this vector space, and a perfectly valid normalized state of the 2-qubit system. Nevertheless, we can't write it as a direct product of some state for qubit A and some state for qubit B. So a state like this that cannot be written as a direct product is called an entangled state. So in next lectures, we'll talk more about entanglement, how we can identify it when we're given a particular state, what are some measures. So there is some mathematical tools and tricks to immediately identify whether a state is entangled or not. All right, this is a good place to stop.